Yes. Now we have aryl halides are basically also known as halogenoarenes. It's basically when a benzene ring has a halogen attached to it. So for example, you have Cl here, you have a Br, you have an iodo attached. These are called what? Aryl halides, or we call them what? Halogenoarenes. Now this right here is called what? This is called chlorobenzene. This right here is called what? Bromobenzene. And you have what? Iodobenzene. So you have chloro, bromo, and iodobenzene. As we go from chloro to bromo to iodobenzene, the boiling points of these aryl halides. So the boiling point increases as we go from chloro to iodoarenes. And all these uh, halogenoarenes, these are oily liquids at RTP. So all of these halogenoarenes or all aryl halides are oily liquids at RTP. So they are all oily liquids at RTP. Where now, if you remember, we did this in previous classes that if you have an electron donating group, if X is electron donating, the incoming group will go on position 2 and or 4. And if X is electron withdrawing, then it will send the incoming group on position number 3. So right here, the X basically is the chloro, bromo, or iodo group. And these are what? Electron withdrawing. Why are they electron withdrawing? They are electron withdrawing because they are electronegative in nature. So since they are electronegative, they will be electron withdrawing groups. And the incoming group will go on position number 3. Now you have a carbon with a Cl here, carbon with a Br, carbon with an iodo. Now we've seen these bonds before in halogenoalkanes, if you remember, but those bonds were slightly different from these bonds. These halogenoarene bonds have two unique features. And let's see their unique features and we'll see why they have those unique features. So these CX bonds, they have two unique features, which are, the first is that these bonds, they are extremely strong. So it is extremely strong. These bonds are extremely strong and therefore resistant to hydrolysis. So they are resistant to hydrolysis because these CX bonds are very strong. And it is less polar than a normal CX bond. So it is less polar than a normal CX bond, and it is extremely strong. So as opposed to a regular C halogen bond, it is less polar and it is more strong. Now let's see why. Why are these bonds stronger as compared to regular C halogen bonds? So we have, I'm taking chlorobenzene as an example. So you have chlorobenzene right here. Now Cl is in group 7 and it has 7 outer electrons. 1 electron is used here to make the bond. This is the second, third, fourth, fifth, sixth, and seventh. You see, you have 3 lone pairs around Cl. Now, these lone pairs are in the p orbital. Why? Because chlorine has its outer electron in the p orbital. So these electrons are in the p orbital. So you have 3 lone pairs. Can I say these are 3 lone pairs in the p orbital? So you have 3 lone pairs in the p orbital right here. Now, let's see what happens. One of the lone pairs from the p orbital, it overlaps with the pi ring. So one of the lone pair in the p orbital. So in the p orbital of chlorine, one of the lone pair overlaps it overlaps with the pi ring. So it overlaps with the pi ring in benzene. So it overlaps with the pi electron system in benzene and stabilizes the CCl bond. So it stabilizes the bond, making it super strong. So what happens is that you have a lone pair here, three lone pairs. Any of these lone pairs, since they're in the p orbital, those lone pairs will overlap. The lone pair in the p orbital will overlap with the pi ring. So there will be extra strength basically provided to this bond because of the orbital overlapping with the pi ring. And this overlap makes the bond stable and makes it stronger. So carbon and halogen bonds, not only CCl, even if I replace it with a Br or an iodo, the bond will be super strong because of the lone pairs overlapping with the pi ring. Now, why is the CX bond less polar in halogenoarenes? This was the first feature, that it's really strong. And I told you why, because of the p orbital overlapping with the pi ring. The second thing is, why is this bond less polar? Now, again, we know that the lone pair overlaps with the pi ring. Yes. So we have the lone pair here overlapping with the pi ring, making it stable, making it stronger. Yeah. So due to the p orbital overlap with the pi ring, what happens is that this carbon that we have, it becomes less positive. Becomes what? Less positive. Why? Because there's a lone pair overlapping with the pi ring. So this carbon becomes less positive. So due to the p orbital overlap with the pi ring, the carbon becomes less positive, or you can say the charge density around the carbon increases. So the charge density increases around the carbon. So since the charge density increases or it becomes less positive, it reduces the polarity or it reduces the polar nature of this bond. Because, let me explain, you know, the CCl bond, a regular C halogen bond, would be polar. This would be partial positive, partial negative. But here in benzene, the pi ring is overlapping with the uh, lone pair. So there is a p orbital overlap with the pi ring. Yes. Imagine this lone pair. Actually, I'm just going to show it like this. So imagine this lone pair overlapping with the pi ring. So since the electrons are being overlapped with the carbon and the pi ring here, what happens is that this carbon, the electrons around this carbon, it increases the charge density, making it less positive, or can I say more negative? So this has become more negative because of the orbitals overlapping with the pi ring. So this becomes more negative. This is also negative. So the electronegativity difference will decrease and the polar nature of the bond will decrease. Is this clear? Due to the orbital overlap, the bond stabilizes, becomes stronger. Due to the orbital overlap, right here carbon around this electron density or charge density increases, making this what? Less positive or more negative. Therefore, the difference between the two will decrease and the polarity will decrease. All right. Now let's see, why does the boiling point increase from chloro to iodobenzene? So I told you that from chloro to iodo, the boiling point increases. And that is because the strength of intermolecular forces, that is the van der Waals forces, will increase. And why does it increases? Due to the increase in the number of electrons. So there's an increase in the number of electrons, making the intermolecular force stronger, therefore increasing the boiling point. Clear? Now let's see the relative ease of hydrolysis. I told you that the bond, the CX bond, is extremely strong and resistant to hydrolysis. We've done hydrolysis in AS when we did halogenoalkanes and we saw nucleophilic substitution with aqueous NaOH. So let's see. Halogenoalkane, let's see the nucleophilic substitution of halogenoalkanes. This is also known as hydrolysis if we do it with aqueous NaOH. We did this in AS. If you remember, this is Rx, where R is an alkyl group, X is a halogen. When this reacts with aqueous NaOH, it makes ROH plus NaX. And this happens in the presence of reflux. Let's take an example. For example, if you have CH3, CH2Cl plus aqueous NaOH, in the presence of reflux, it will become CH3, CH2OH plus NaCl, right? Now, if you remember, I told you in AS that the ease of hydrolysis depends on the nature of the CCl bond and the type of halogenoalkane, whether the halogenoalkane is primary, secondary, or tertiary, and the nature of the CX bond. Which CX bond will break the fastest? The fastest would be Ri. Yeah. So the ease of hydrolysis depends on the nature of the CX bond. So the ease of hydrolysis will be the fastest for iodoalkanes. Why? Because in iodo, the bond length is greater. Therefore, the bond strength is weaker and is why they will hydrolyze the fastest. So this will hydrolyze the fastest as opposed to bromoalkane, which will be relatively slower, and the slowest will be chloroalkane. Why? Because this bond is the strongest. And why is the strongest bond? Because of greater bond length. So you have greater bond length, therefore this is the strongest bond. And this is a weaker bond. And why is this a weaker bond? Because it has the shortest bond. Oh God, this is the weakest bond because it has the longest bond length. You know, bond length is inversely proportional to bond strength. And this is the strongest RCl bond due to shorter bond length. And we know as the bond length increases, the bond strength decreases. Yes. So right here, your iodoalkane will hydrolyze the fastest. We've done this in AS. We've seen hydrolysis in AS, right? Nucleophilic substitution of halogenoalkanes. And which one will break the fastest? Iodoalkane. Now, if I do the same thing with halogenoarenes, where you also have a C halogen bond, if to this you add aqueous NaOH, there will be no change or no result, or there will be no reaction. Why? Because the C halogen bond in halogenoarenes is very strong. So here the C halogen bond is really strong, is why there will be no reaction. Yes, halogenoarenes, they are resistant to hydrolysis. Is this clear? Do you guys understand? And we know why are they resistant to hydrolysis? Because of the strong bond. Why is the bond strong? Due to the lone pair overlapping with the p orbital, the pi ring, the p orbital overlapping with the pi ring. Let's see. So we have methylbenzene reacting with concentrated HNO3 and concentrated H2SO4 to make 4-nitro-methylbenzene. So this right here is what? Mononitration of methylbenzene. Yes. So you have mononitration of methylbenzene, and we know this happens at 30 degrees Celsius. They are saying that and another isomer of 4-nitromethylbenzene is formed as a byproduct. Draw the structure. Now you know that the methyl group is what? Electron donating group, and it directs the incoming group on position number 2 and on position number 4. So they've already shown 4-nitro, so the other byproduct or the other product would be what? A 2-nitromethylbenzene. Yes, so the other product would be 2-nitromethylbenzene, which is also, you can see, a positional isomer of 4-nitromethylbenzene. Then they're saying write an equation for the reaction between HNO3 and H2SO4. So this right here is going to make what? A nitrating mixture. So let's see the reaction. You have H2SO4 plus HNO3 giving you 2HSO4 minus plus NO2 plus H3O plus, the equation to make the electrophile. Describe how the bonding and structure of the six-membered ring in the intermediate differs from methyl benzene. You know that in methyl benzene, all carbons are sp2 hybridized. So in methyl benzene, all carbons are sp2 hybridized. Yes, they are sp2 hybridized, therefore the structure is planar. And in the intermediate T, you have an sp3 hybridized carbon, right? It is anyway a carbocation with a positive charge. Yes. And this will be what? Since one of them is sp3 hybridized, it would be tetrahedral in shape. Yes. And you have 5 other carbons which are sp2. So other carbons are sp2, and you have one carbon which is sp3 or tetrahedral. This will be a 4-valent carbocation. Clear? Is this understood?